joining us for the IEEE Computer Society Standards webinar series, brought to you by the Standards Activities Board. With over 225 standards that transform the way we live, work, and communicate, the IEEE Computer Society sets the standard for design automation, simulation, testing technologies, Ethernet and Wi-Fi, quality assurance processes, systems architecture, DevOps, and more. Standards deliver best practice processes for developing market-ready interoperating systems, products, and services. You can have an impact by joining one of the over 200 IEEE Computer Society Standards working groups. Participating in one of the working groups grants you access to information that reduces risks, increases proficiency, and shapes the future of the industry. Help determine what's next in computing technology. Learn more about our standard working groups at computer.org/standards.
Hello everyone, thank you for joining us today and welcome to today's webinar, IEEE 802.1 Data Center Network Standard, Enabling Data Center Fabric Convergence onto Ethernet, by Lily Yunping Liu from our Standards Activity webinar series. My name is Scott Levine. I'm the membership manager here at the IEEE Computer Society and will be host and moderator today. Before we get started, I'd like to address some housekeeping items. This webinar is being recorded. You'll receive an email tomorrow, which will include a copy of the slides as well as the recording. You can ask any questions in the Q&A box you see on your screen. If possible, please reference the slide your question refers to. Lily will answer as many questions as she can following the presentation. IEEE Standard 802.1 is just one of the many standards founded by IEEE. Keep up with our ongoing calls for participation and get involved with the Standards Activities Board. As part of this network, you'll connect with professionals from all over the world and share your expertise within the field. Visit computer.org to find ongoing information and participation from this standard and many of our other standards. Circling back to today's topic, IEEE 802.1 standards apply to a broad set of industry verticals. One such vertical is the ever-important data center network that fuels today's digital transformation of the cloud, mobility, and Internet of Things. More than 20 years ago, IEEE 802.1 created a set of standards which enabled the convergence of data center technologies onto 10 gigabits per second Ethernet. Currently, the Ethernet fabric in the data center needs dramatical expansion in size and performance to address the requirements of high-performance computing and artificial intelligence applications in hyperscale data centers running on 400 gigabits Ethernet and beyond. Among the many activities within IEEE 802.1 is the working group is tasked to address these needs of the minor hyperscale data centers. This webinar will provide a historical view of the evolving data center network technologies and a deep dive into their current and ongoing projects. As mentioned, joining us today is Lily Yunping Liu, who is a standard engineer at Huawei Technologies and works on the data center network innovation team. She has over 15 years of experience in the telecom industry plus data communication technologies, including Wi-Fi, campus LAN, and data center network. Prior to Huawei, she was a development and verification engineer at Ericsson, leading the test strategy of continuous integration projects. She is the editor of IEEE P 802.1 QDT, PFC enhancement project, and an active technical contributor to the 802.1 DCN projects, which you'll hear about today. Lily, thank you again for joining us, and the floor is yours.
Okay, thanks, Scott, and thanks IEEE Computer Society for the opportunity to present our standard work. In this presentation, I will introduce IEEE 802.1 data center network standards, including a brief review of the history and the new wave of standard development in recent years. Well, you may know that IEEE 802 standards emphasize the functionality of the lowest two layers of the OSI reference model, the physical layer and the data link layer. When we look at the IEEE 802.1, it is a working group under IEEE 802 Standards Committee. It works in 802 LAN architecture, internetworking among 802 LANs, MANs, 802 security, the overall network management of 802, and some protocol layers above the MAC and ARC layers like STP. IEEE 802.1 that includes several task groups like DSN. You may know that it is very famous now, and it also has security task group. It used to have the data center bridge, the DCB task group, where it's a place to develop the data center related standards. Now such work has been merged to DSN task group. Another activity organized by IEEE 802.1 is NANDICA. That is the IEEE 802 Network Enhancements for the Next Decade Industry Connections activity. NANDICA actually provides an efficient environment for building consensus and developing many different types of shared results like white papers, the reports, etc. Such activities may complement, supplement, or be precursors of IEEE standards projects. So IEEE 802.1 developed standards for data center fabric since the year 2006. Before 2006, we say it is traditional Ethernet data center. At that time, the key requirement is low cost. People cared about cost reduction. It uses TCP/IP to provide the best depth transmission. Later, Ethernet bandwidth increased a lot, entering the GE era. That, I think, laid a solid foundation for Ethernet to carry more services. So people start to think about Ethernet for storage workloads. At that time, storage fabric used the fiber channel, the FC, as the main protocol. But leveraging Ethernet fast speed and its mature ecosystem, FC over Ethernet, this technology was developed. Then the storage fabric and the traditional data center fabric are converged onto the Ethernet. But the traditional Ethernet cannot prevent packet loss, which was very important for storage workloads. So several standards of Ethernet were developed in IEEE 802.1, including .1 QBB, the priority flow control, PFC, .1 QAU, congestion notification, or you may be more familiar with the name QCN, and .1 QAZ, enhanced transmission selection, ETS. We call the Ethernet in this period as Converged Ethernet, Converged Enhanced Ethernet. The CEE is the short name. Then I will quickly go through the three standards in the following slides. First, PFC. PFC is widely used today. It is a link flow control mechanism. We know in IEEE 802.1Q, it defines 8 priorities. So PFC is performed on a per priority basis, pausing transmission of data frames associated with one or more priorities for a specified period of time. And it can be enabled for some priorities on the link and disabled for others. The right figure shows the implementation example. The XOF threshold, which invokes PFC, is set on each PFC-enabled priority. In this figure, it is priority 5 and priority 6. Then priority 6 reaches the threshold XOF. PFC pause frame then is triggered and sent upstream. As a result, the upstream priority 6 transmission is stopped. This is a PFC. Another congestion management mechanism is QCN. The principle is like this. When the congestion point, or we call it CP, detects congestion according to the CP algorithm, it generates congestion notification message, CNN, to the reaction point, we call it RP, causing the reaction point to adjust the flow control. The congestion point algorithm in the right-hand side box It uses FB to capture a combination of queue size excess and the rate excess. When FB, the value of FB is negative, it means the buffer is oversubscribed. Otherwise, there's no congestion and no feedback messages are sent. In case of the congestion, the CP, the congestion point, selects a frame from the incoming stream with a probability. This probability depends on the severity of congestion, and CP sends a feedback message that is CNN to the source of the selected frame containing the value of FB. The value of FB is quantized to 6 bits before transmission. Then looking at the reaction point side, the algorithm is shown in the left box. When the RP receives the CNM, it decreases the sending rate according to the FB, which is included in the CNM message. Then how to increase the rate? There is an algorithm. The figure in the box depicts the algorithm. It has 3 stages: the fast recovery stage, active increase stage, and hyperactive increase stage. The rate increase in the 3 stages depend on 2 factors. One is byte counter and another is timer. The 2 factors work independently, and the status of the 2 factors, the byte counter and the timer, they decide which stage the RP is in. And different stages have different rules to increase the rate. Regarding the detailed algorithm, I think you can find them in .1q specification. So QCN, when it is designed, is only designed for layer 2 network. So that limits its usage in data center, which is dominated by layer 3 network later. However, this does not affect the fact that there are still many merits in its algorithm. Like DCQCN that emerged later is the good example. This is a QCN. Another representative technology in CEE in Converged Enhanced Ethernet is this enhanced transmission selection. ETS allows dynamic bandwidth allocation among traffic classes on a single network. It allows 1 or more priorities to be assigned to a traffic class. It's shown in the left figure. Several priorities are assigned to traffic class 1 for LAN service. Priority 3 is assigned to traffic class 2 for storage traffic. And another 2 priorities, priority 6 and priority 7, are assigned to traffic class 3, which is for the compute clustering. When the offered load in a traffic class doesn't use its allocated bandwidth, other traffic classes can use the available bandwidth. As shown in the right figure, T2 time slot. In T2 time slots, the blue traffic class uses additional 1 Gbps available bandwidth. And in T3 time slot, it shows the offered traffic of blue traffic class exceeds its allocated bandwidth, and at this time, there's no available bandwidth, so some traffic of the blue traffic class has to be dropped. Well, that is what the CEE already have, but the world is always changing. Digital transformation is driving changes in our lives, driven by new emerging applications like the autopilot, intelligent manufacturing, etc. A large number of data will be generated during the digitalization process. The IDC predicts the global data will grow from 45 zettabytes in the year 2019 to 175 zettabytes by the year 2025. However, data is not the end in itself. Computing systems in data center are needed to extract knowledge and wisdom from data. In order to handle the large amount of data, computing systems are upgrading rapidly to provide enough computing power. So looking at the right figure, the computation scale keeps increasing. The HPC or supercomputer system performance has already reached EFLOPS. Now it is going to break through 10 EFLOPS. And another category in computing is AI. AI is very hot today. ChatGPT brings AI a lot of attention to people. The AI model size grows fast. GPT-3 has 175 billion parameters. When it comes to GPT-4, the parameter size grows to 1.76 trillion. That is very huge. Meanwhile, the storage involves its media. SCM latency is about 1/10 of SSD, and the storage system is from HDD-centric to SSD-centric, now is moving to the memory-centric. So, data center fabric as the connection component in the whole system should not become the bottleneck. It has to match with all these changes. Now I will talk a bit more about the computing systems changes on this slide to see the impact on data center fabric. First, look at the AI. AI, the large-scale AI model, LLM, large language model, which is very popular today. It uses data parallelism and model parallelism. Looking at the table, the data parallelism DP, it requires inter-nodes communication, typically uses collective communication or reduced operation. The traffic is about gigabytes level. Then model parallelism has different types. Inter-node communication usually uses the TP, the tensor parallelism, which is model parallelism. It requires hundreds of gigabytes level bandwidth for traffic. That is a very huge bandwidth requirement. But now it uses bus technologies for communication like NVLink. Then PP, the pipeline, extends on simple task parallelism, breaking the task into sequence of processing stages. Each stage takes the result from the previous stage as input, with results being passed downstream immediately. So it requires inter-nodes communication by the send and receive operation. The traffic is from hundreds megabytes to gigabytes level. Next model parallelism is MOE. That is also very important today. MOE is short for mixture of experts. It has gigabytes level inter-nodes traffic. So from this table, we see AI application is bandwidth hungry. High throughput fabric is critical. Another characteristic of AI traffic we must pay attention is that the traffic is always the burst of flows, and the flow number is low. That means low number, but each single flow is big size. That brings the challenges on load balancing. Then the next box is for the HPC. HPC uses HPR to evaluate performance. HPR is the classic benchmark used in top 500 list. Here in this figure, the Rmax divided by R peak value is the index to check the effectiveness of the system. Rmax is the max HPR performance in practice, while R peak is a theoretical value. We can see both the bandwidth and the latency are keys to HPR performance. But when the bandwidth is fixed, we could see reducing 1 microsecond can increase 2 to 3% performance of the HPC systems, which is very significant for HPC systems. Actually, if we say, we can say the AI is sensitive to throughput, but HPC is more sensitive to latency. Because HPC is dominated by small size messages, I remember from some MPI usage analysis on some production supercomputer, it shows most messages in the HPC system are less than K bytes. And for some typical operations like reduce and bcast, even more than half the messages are below 64 bytes. So such small messages are very sensitive to latency. This is for the HPC. Then for the cloud, cloud computing. Cloud computing focuses on the elastic architecture to achieve better resource sharing. It is moving from the computing pod, storage pod to the resource pooling architecture, such as the GPU pool, memory pool. But the resource pooling requires sub-microseconds latency and determinism. This is also a challenge to Fabric in cloud. Finally, let's look at the storage changes. The number of front-end access to the storage systems can reach hundreds of thousands. And the IOPS of the storage system is increasing from 1 million to 10 million. And the new storage media, as I mentioned in the previous slide, is much faster. So a large scale and a low latency fabric is needed in the storage system. These are some changes for in the world in the computing systems. And there's another trend we should notice, that is the convergence of the AI, HPC, and cloud computing in data center. HPC is available as a cloud service in many public offerings like AWS, Alibaba, etc. And HPC-based AI are fast in emerging markets with 31% CAGR, the compound annual growth rate. And we also see that Microsoft started AI for science to empower the scientific discovery. So all these high performance applications are converging. Then we need a converged fabric to meet the application's requirements. The converged fabric should be large scale, high throughput, and low latency. CEE, the Converged Enhanced Ethernet, has a good start, providing lossless fabric to storage workloads. But today, with the computing power explosion, CEE-based fabric needs involvement so to carry today's storage workloads and computing workloads in data center. Maybe this involved CEE can be called hyperconverged Ethernet. The hyperconverged Ethernet should fully utilize the physical network resource, like using efficient load balance to achieve high throughput and using improved congestion control or flow control to reduce the latency. Although Ethernet is stepping into 800 gigabps, 800 GE, or even 1.6T GE, bandwidth is still a precious resource. Tightly coupled networking and computing is another direction worth to exploring, like topology of thing computing, computing of thing topology, compute and network co-design stack, etc. So in this way, to minimize network resource for computing tasks while minimizing the completion time. This is what we are seeing happening in the world today. Back to IEEE 802.1, it has already sensed the changes and started a new wave of standard development. The new wave is driven by computing workload, as we talked just now. The requirements of Fabric is large scale, low latency, and high throughput. Different protocols will run on the Fabric, like NVMe over Fabric, Rocky, as well as TCP/IP. In order to support those new requirements, IEEE 802.1 started new work since the year 2018. It includes NANDCA reports and standard projects. I will introduce them one by one in the following slides. First, the NANDCA reports. NANDCA reports discuss future opportunities in data center fabric. Until now, IEEE 802 has published 2 reports. One was in the year 2018 and the other was in 2021. The later one extends the first reports, providing additional background on involving use cases in data centers and proposes solutions to additional problems. And from these reports, it has also incubated some standard projects. You will see that later in the slides. In the NANDCA reports, some new use cases are identified, including the online data-intensive service, deep learning, NVMe over Fabric, and the cloudification of the central office. There are massive amounts of data and and computing in data center, a lot of innovations are emerging in storage, compute, and Ethernet ports. Data center fabric challenges primarily focus on congestion that was described in the reports. With the massive data computing and massive messaging, the fabric is easy to get congested. As a result, congestion degrades application performance by causing packet loss, latency loss, or throughput loss. Nandica reports analyze the gap of current congestion management solutions. First, the ECMP. ECMP is used in class topology. It is a very popular solution for load balance. It selects a path by hashing the flow identifiers. This is a simple mechanism, but it does not consider whether the selected path itself is congested. It is quite easy for hashing multiple flows on the same path, resulting in overloaded links. ECMP collisions is a serious problem in AI training. To address the issue, load balance design space is shown in Nandica report. Centralized approach have difficulty to scale and to meet real-time latency requirements. Then a global view of the network can provide more information than the local in-switch decisions and requires efficient means of obtaining congestion notification from the network. Then the granularity. The granularity of load balancing has trade-offs between uniformity of the distribution and complexity associated with assuring data is delivered in its original order. Another common way for congestion management is PFC and ECN. PFC has some well-known drawbacks like head-of-line blocking, deadlock, and ECN does not give the instant reaction to congestion because it relies on RTT, the round-trip time, as a control loop. Large-scale fabric leads to longer RTT, therefore introducing longer control loop delay. Another problem is that the configuration of PFC and ECN is complicated. Appropriate threshold for PFC and ECN should be set, otherwise the performance will suffer, but the manual way will not work, especially on large-scale fabric. There are some future technologies proposed in Nandica reports to address the gaps. I will not go to detail about those future technologies in this presentation, but if you are interested, you could download the reports and read. Then among those proposed technologies, 3 directions have been incubated as standard projects in IEEE 802.1 till now. They are 802.1 QCZ, congestion isolation, 802.1 QDW, source flow control, and .1 QDT PFC enhancement. I will introduce them in the following slides. First, this is a congestion isolation .1 QCZ. This project was initiated in November 2017. It has been published this year. This is the amendment to .1 Q. Congestion isolation can work in conjunction with higher layer end-to-end congestion control. It reduces the frequency of relying on PFC for lossless environment. The congestion isolation, or we call it CI, it addresses PFC head-of-line blocking issue. As the Ethernet data center network scales in size, speed, and number of concurrent flows, head-of-line blocking issue is more serious. In this figure, the red flow is identified to cause congestion, so the red flow is congested flow. When PFC is issued, the blue flow and red flow are all stopped because they share the same queue. So the blue flow is the victim flow. Obviously, PFC increases jitter and the latency of the victim flow. When the victim flow is the mice flow, the small flow, that is especially harmful. Head-of-line blocking also increases frequency of congestion spreading. This results in more victim flows and potential PFC deadlock in heavily loaded fabric. The principle of congestion isolation is to isolate congested flow to a separate queue. The main procedure is like this, as shown in this figure. The first step, the congestion point identifies the flow causing congestion and isolates the congested flow to a congested queue locally. The second step, when the congested queue fills, the congestion point sends a message we call it CIM. The CIM message is sent to its upstream neighbor. The third step, when the node receives CIM, the upstream neighbor isolates the same congested flow in a separate queue, eliminating head-of-line blocking. If the congested queue on congestion point continues to fill until PFC threshold is reached, the congestion point invokes PFC to upstream. In this way, head-of-line blocking is mitigated and PFC frequency is reduced. This is the congestion isolation. The second new project is PFC enhancement. It is still in task group discussion. Draft 0.2 is ready now. This project emphasizes the requirements for low latency and lossless transmission in large scale and geographically dispersed data centers. This project covers two features. One is PFC security enhancement, the protection on PFC frames by MACsec. The other feature is the PFC configuration enhancement, providing the automatic calculation for PFC headroom. So let me first explain what is the headroom. We know in most implementations, XOF threshold is set on priority queue to invoke PFC. Then there's a time delay between the PFC invocation on PFC sender and pause action on PFC receiver. This delay requires the PFC sender reserve some buffer to absorb in-flight packets. This reserved buffer is called headroom. Now, I will first introduce the PFC security enhancement. Currently, PFC is not protected by the MACsec because PFC pause frame is only used within a data center, and data center is a secure domain. People do not worry about the security problem internally. But a new use case appears as shown in the left-hand side the figure. Rocket V2 is used for data center interconnection. Rocket V2 need to use PFC to avoid frame loss. In this case, PFC frames have to traverse public land. It brings security concerns. Now, the current protocol layer do not support PFC frames encryption. PFC frames directly go to the MAC control layer through MAC control through the MAC control path as shown in the right-hand side figure, the first figure. But in this view, you can see that the MACsec module is on MAC data path. So PFC frames cannot be protected by the MACsec because it does not go to the MACsec module. In order to protect PFC frame in the DCI data center interconnection case, some early implementations of MACsec were implemented externally to the MAC, such as within a PHY, the physical layer as a bump in the wire, as shown in the right-hand side figure, the second figure. In this way, it actually encrypts everything coming out of the MAC. This is not compliant with 802.1 AE, the MACsec standard, and it has some interoperability issues. So we need to do something with that. A new PFC scheme is proposed to enable protected PFC frames. It has minimal impact to current PFC implementations. This PFC scheme supports data mode and control mode. In control mode, scheme passes through existing MAC control interface with no delay. When in data mode, the scheme generates and consumes PFC frame by converting the MAC data primitives and MAC control primitives. This may introduce some delay, and when we do the PFC headroom calculation, the delay will be included. So that is the first feature in PFC enhancement regarding the security. The second feature is PFC configuration enhancement. The problem is current manual PFC headroom reservation in network management is not efficient. PFC headroom calculation should include several parts. One is the meter delay or cable delay. This is related to the link length. Another is internal processing delay. This is related to different implementations and Ethernet port speed. Fixed delay is to consider the worst case. If we reserve less buffer than required, that will lead to a packet loss. But if we reserve too much buffer, that also causes the buffer waste. Because the cable delay and internal processing delay are variable depending on different deployment, like port speed, cable length, different vendor implementation, the manual configuration will be complicated, even impossible to get appropriate headroom value in large-scale data center and or the long-distance data center interconnection. This is why we need automatic way to do this. We use a point-to-point round-trip measurement to get adaptive PFC headroom value. In left figure, it shows the timestamp points we need to measure in order to calculate the headroom. In the PFC enhancement project, it plans to include two modes for the measurement. One is non-PTP-based mode, another is PTP-based mode. The non-PTP-based mode specifies a new request response measurement to measure the round-trip delay, and the piggybacking mechanism is considered to complete the measurement faster, especially in request loss case. Then the PTP, another mode, PTP-based mode, it is intended to use to be used in the PTP-activated data center fabric. If the data center fabric already supports the PTP, then we can use this mode. The basic idea is to reuse PTP protocol, specifically the P-delay procedure, to measure the cable delay, then develop additional procedure like DCBX enhancement to request the peer node to feedback the internal processing delay. Finally, sum up the cable delay, the internal processing delay, and the fixed delay to get the headroom. Actually, this is not a straightforward way to calculate the headroom, but it can leverage existing PTP spec. So each of the modes can be used in different scenarios. The next project I'd like to introduce is source flow control. The discussion of this technology was initiated in the year 2021, and the project was set up in 2022. And now it is in the individual contribution stage. The target of SFC is to reduce latency in large-scale data centers when the congestion control is less effective. We aim to let SFC work in conjunction with other congestion controls such as DCQC congestion isolation, and it supports layer 3 environments. One more thing I want to mention is that in the scope, it provides a possible way to make it work without server upgrade for early deployment. We could see that in the next slide. SFC mainly solves in-cast congestion. We know that in-cast congestion is a many-to-one traffic pattern happens at last hop. The tail latency is impacted. End-to-end congestion control and hop-by-hop flow control are current solutions. The NANDICA reports have already analyzed the problems of current solutions. For example, the transmission side for this end-to-end congestion control, the transmission side needs sub-RTT reaction to adjust the sending rate. That is because the fast link speeds enable shorter RTTs to complete the messages. But end-to-end congestion control represented by DCQCN relies on the forward signals. First, the data packets carrying the signals may be delayed due to congestion. Second, the sending rate cannot be adjusted until at least one RTT has passed and may need multiple RTTs to flatten down the rate curve. so such mechanism cannot take action in time. Then looking at the flow control, PFC is the typical hop flow control. It can react immediately when congestion is detected. It guarantees no packet loss when properly configured, but it also has negative effects, just like the head-of-line blocking, the PFC deadlocks, and sometimes the malfunctioning device may also cause PFC storm throughout the whole fabric. So SFC is the new congestion management method, not only give a quick reaction, but also eliminate the PFC drawbacks. So what is the idea of the SFC technology? The basic idea is to invoke PFC on the source side directly when congestion is detected. So looking at the left figure, when in-cast congestion happens, the congestion point identifies the congested flows, then sends SFC message to traffic source. The source side should pause the traffic when receiving SFCM. It is possible to have per flow basis pausing at the source side. The SFC can be combined with congestion isolation. That means congestion point first isolates the flow. If the congestion persists, the edge to source signal, the SFCM, is sent to the source using the layer 3 message. An alternative way to deploy SFC in the field is the SFC TR switch proxy mode, as shown in the right figure. In this mode, the TR switch intercepts SFCM at egress port connected to non-supporting host using the egress stream filter matching SFCM UDP port number. Then generates traditional PFC frame from the SFCM towards the source. Then what information should be included in SFCM is still under discussion. The basic idea is it should include the source IP, the destination UDP port, post duration, and DSCP. But that needs further discussion in the project. We will see in the future. The two modes, each of them has its own advantages. SFC without proxy can have a fine-grained flow control, but SFC with proxy can speed up the deployment in field because PFC has already been widely deployed. We do not need to make any changes on source hosts, just the simple interaction between the switches, and do not need new protocol between the switch and the host. So this is the SFC idea. This is some new work about data center fabric in the 802.1. The final page, let me make a short summary. Now we are in a new period. Explosion of computing power growth ignites another wave of network technologies innovation in data center. Following this CEE, the Converged Ethernet, Converged enhanced Ethernet standards, IEEE 802.1 has started new standardization work, developed and developing new projects to meet the emerging applications needs. It is expected to see more work happening in IEEE 802.1 for the hybrid converged Ethernet. It is also very important to have more coordination between IEEE 802.1 and other standard organizations to finally enable data center fabric convergence onto Ethernet. So that is the presentation. Thanks. And I'd like to take the questions.
Thank you, Lily. That was a great presentation, a lot of great information and detail in there. As Lily said, and as we said, please type your questions into the Q&A box you see on your screen, and we'll start going through the questions that we got so far. Let's see, the first question is from Bing. They asked, what port number is SFCM UDP port uses? What protocols does the source and destination communication use?
Okay, The UDP port is not decided yet. Basically, we want to apply a new UDP port to be used for the SFCM. And regarding the protocols for the source and destination, actually, that is the new protocol because we need to develop the whole mechanism when the congestion is detected on the congestion points, then the SFCM message will be generated. So that is something new for the network. So is that something you want to ask?
No, I think that's great. Our next question from Pavanthon asks, how is the standard related to IEEE TSN standard?
Actually, no relationship with the TSN technologies because TSN is for the industrial or for the automotive, the cars, or just for the cars. But those traffic has different pattern as the data center. So data center has its own characteristic. It uses some new technologies. So that is not something with the TSN standard. But the work, the discussion are within the TSN task group. The technology is different, just organized by the TSN task group. So that's the relationship.
All right, perfect. Caroline chimed in and wanted to thank you for the great presentation. And as I said, I echo that. We have no additional questions at the moment. So if you want to have any final thoughts, and we can see if any final questions come in. So Lily, do you have any final thoughts or comments you want to
add? Not from me.
Okay, that's fine. Yeah, no, you covered a lot of ground, so just wasn't sure. So I think with that, we'll wrap up the webinar. Thank you again for Lily for all of her great insight. I would like to thank everyone for attending the webinar today. Before we wrap up, just a quick programming note on our upcoming webinar schedule. On October 12th, we have a webinar from our Build Your Career webinar series, how to be a successful manager as an introvert. On October 26th, also from this series, the Standards Activities Board, we have Zero Trust, Changing the Security Paradigm. And then on November 16th, from going back to the Build Your Career webinar series, we have a webinar on demystifying agile project management. You'll be able to register for all these webinars and some of the most recent webinars that are on demand using the link you receive in tomorrow's email. That will again include the slides in the recording. Again, I want to thank all of you for attending, and once again, Lily for joining us and sharing her insights with us as well. Thank you again, and have a great rest of your day.